Welcome to the Build Test Solutions monthly webinar series. This instalment, titled Buildings Behaving Badly, will focus on the performance gap between how buildings should be performing and how they are actually performing in the real world, and how we can overcome this with testing. The session will be presented by Richard Jack, our Technical Director, and he will be joined after his presentation by Rachel Brain, our Customer Relationship Manager, for the Q&A at the end.
Thanks everyone for coming. So buildings behaving badly, I won't attempt to do the theme tune, and it's going to be a presentation all about the performance gap, what I mean by the performance gap, some previous field trial studies, and see if we can figure out some of the reasons why there is a gap between predicted and actual performance in buildings. Let's get going. So to give you an introduction, you probably know who we are already, but Build Test Solutions, our whole game is our strapline we say to ourselves is make measurement mainstream. So our whole game is to make building performance measurement tools, and we're trying to make them both as accurate and as accessible to users as possible, so that we can make measuring buildings a totally normal part of building and retrofitting. I always think it's crazy that buildings are basically the most valuable asset that we have, and they've got less quality assurance on them than my biro. So what we want to do is make sure that we can see if they're actually performing as we expect and hope that they are. So we've got several different tools for measuring overall building heat loss or heat transfer coefficients, and there's going to be an explanation of what that means. Air tightness, U values, mold risk, and the whole game is to make those as accessible as possible. So our users, we've got good coverage all over the UK, a couple of hundred users, which is a real delight, and they're our allies in making measurement mainstream. And there's basically two different ways that people access measurements from our products. The first we call measurement as a service. So that's sort of a familiar way of accessing surveys or measurements. And it would be building professionals going to a building, using the tool, carrying out a measurement and providing the result to a client. And then we have a second set of users who we call integrators. And these are people who are collecting data in buildings already, like smart meter data or temperature data, and then using algorithms that we're providing to add additional value and insights to that data. So there should be lots of ways to access the measurements from the tools that we provide. And we're not really a measurement provider, we're a measurement tools manufacturer, but we always want to be able to connect people to people to be able to access those measurements in a sort of scalable way. So what I'm going to cover today is what a heat transfer coefficient is, how they're calculated and measured, and what the difference between that is, and how and why the predictions and the measurements differ, and why that might matter for how we think about buildings. So a heat transfer coefficient is a measurement of all the heat transfer paths for a building. So it's a good measure of the amount of the rate of heat transfer between inside and outside of a building. And we use the term transfer instead of loss because it works both ways round. So on a day like today, it's certainly cooler in here than it is warmer outside my house. So I'm transferring heat outside, and the HTC of the building determines the rate at which that happens, as well as the rate at which I'll lose heat in winter. So whenever an energy performance certificate is generated, we calculate the heat transfer coefficient. And the way it's calculated is to measure the area of each element of the building and multiply it by an assumed U value for that building element. And then also to calculate the amount of heat transfer by air movement, either by accidental air movement, infiltration, or deliberate ventilation. Or we could measure that HTC in situ, and what I want to get into today is how good are the estimates that we're using to generate EPCs. So the HTC in RDSAT, so reduced data SAT, the algorithm, the calculation method we're using to generate energy performance certificates, it isn't a highlight metric on the EPC. so you won't see it on your standard energy performance certificate, but it's calculated for every EPC assessment. And as you can see in this chart, this is an example semi-detached house, and the HTC and the EPC are directly linearly related. So the greater the HTC, the greater the heat transfer, the worse the EPC rating. And if I'd done a similar chart for the energy costs or energy demand or CO2 emissions, they would all show that same relationship. So that HTC is totally crucial in determining how energy efficient the building is calculated to be. And any inaccuracy in the HTC will directly impact all the outputs of that EPC. Sounds like some people have had access issues, but happy you're here now, and we'll take that on board and try and make it a bit easier next time. Okay, so what is Smart HTC? It's a tool to measure HTCs, and it's an in-use energy balance. So what we're doing here is, rather than measuring all the little heat losses or heat transfers from the building, we measure how much energy consumption there is, and we measure the internal temperature that delivers and use that to infer the amount of heat transfer. I think of it a bit like a leaky bucket. So instead of measuring the size of all those little holes, we measure how much water we pour in the top, but instead of water, we're talking about heat. It's limited to use during winter. So we're looking for a significant amount of temperature difference between inside and outside so that there's enough heat transfer for us to accurately measure. And we want 21 days worth of monitoring data during winter. Ideally, that would be energy consumption data or energy inputs to the building and internal temperature data. If you only have energy data, we can actually still estimate the HTC with a reasonably high degree of accuracy, but not with the same degree of accuracy that you get with the internal temperature data. It's a cloud-hosted calculator, so it's a bit of software that lives in the cloud, and you can access it either through a pretty easy-to-use user interface on a browser, or our integrators would be accessing it via APIs, so automatic connection with the calculator so that it can be integrated into their software platforms. So that's Smart HTC. It's been available since 2021, and we've done over 11,000 measurements since it's been available, and we've got over 100 users, and you can see that there are quite a few different groups of people here. So we've got some sort of researchers, consultants, surveyors, and then installers, and then some integrators as well. So people collecting data and putting that data to good use. And as I described earlier, there's two business models that people are using to provide the measurements, either measurement as a service or that integration where it's integrated into something like a smart thermostat or your smart meter. Just to give a bit of credence to the performance gap studies I'll introduce later, I wanted to include this to say that we've done quite a lot of validation of Smart HTC over several years. So in this chart, you can see 43 comparisons with a baseline measurement by a co-heat test or an aggregate heat loss test. It's quite a mixed sample, so that you can see down the bottom left there, you've got some really low HTCs there, passive house level flats, right up to large houses with quite poor thermal performance. And you can see we're getting really good agreement across the piece. We've got really good accuracy. Here, a 0% value would be perfect agreement, and that's a stat called the net mean bias error, and it's measuring if there's a bias towards over or underestimation. So you can see that we've got a net mean bias error of 1%, which means really high accuracy, and we've got pretty good precision. So 12% is reasonably good for this. If we did the same analysis for a calculation method, we'd be looking at 30% or above. So we still think we can get a bit better with that, but it's got pretty high precision as well. So I introduced that just so to give you some reassurance that the performance gap studies I'm going to introduce now are pucker. So the first one I want to talk about, performance gap, and here I'm talking about the HTC as measured or as predicted in RDSAP. This is a project we did for DESNZ, Department of Energy Security and Net Zero, with the Energy Savings Trust, led by the Energy Savings Trust. And so this is a performance gap study of 503 buildings. It's the biggest ever, and I'm excited about that because I know what sample sizes we've worked with before, but the Energy Savings Trust are used to working with stock level sample sizes. So for them, 503 was a tiny number, and that reflects the challenge we've got to try and get more HTC measurements in buildings. The sample's biased towards older buildings, and it's also got a lot of flats and semi-detached houses in there, so it's not a representative sample, but it is a pretty mixed sample of different buildings. The Energy Savings Trust generated the RDSAP HTCs for this performance gap study, and that's actually a lot more difficult than it should be, because although the HTC is calculated for every EPC, it's not stored. So we can't access it later for comparison, and not even all the required inputs are stored. So that's something really easy that we could change about how we generate EPCs, so that when we actually do a measurement, we have a comparison value to compare against without having to do a lot of legwork to reproduce it. So here's the results. And the first thing when I saw this chart was I was really disappointed that there was a clear relationship between the measurement and the calculation. I thought that it would be a total point cloud, and it would mean that the calculation never worked, which is a real measurement fan. Felt like a good thing. But once I'd sort of got to terms with that, I thought it was really interesting that actually there is a clear relationship here, a clear statistically significant correlation. So RDSAP is doing okay at categorizing buildings, but actually more than half of all of these 503 buildings that calculated RDSAP was outside the confidence interval of the measurement, so it was wrong, which is also pretty crazy. So even though there's a good correlation for individual buildings, you can get differences. It was more common in this sample to overestimate the amount of heat loss. So the buildings were actually better than expected, which is a little bit different to some of the studies we'd seen previously. And there was an average performance gap, so the average absolute difference between the prediction and the measurement was 30%. But it was interesting that there were quite commonly large errors. So for 1 in 6 of these buildings, the gap was more than 50%. So the building was 50% different to expectation. And this slide is sort of expanding on that a little bit. So you can see the distribution of performance gaps. You can also start to see the limitations of a sample size of 503 when we break down into rating bands, because some of those sample sizes are quite small. But you can see there's not a really clear relationship where buildings are different at different SAT rating bands, pretty consistent across all those SAT rating bands. And that pie chart is just showing again that it's pretty common for there to be really quite large gaps between the prediction and the measurement. Now, I wanted to compare this to some previous performance gap studies, and these are done by Leeds Beckett University, one of the originators of in situ performance measurement, and from the SMETA project run by DESNES, and from the Building Performance Network State of the Nation project. So that's all of the results from all of those projects combined into this chart. And just taking a first look at the chart, the first thing I notice is the trend line looks very similar, although there's here more data points above the solid black line, which is an x equals y line. So what's happening here is we've got a total sample size of 84, and here we've got a strong bias towards new builds. In this case, 70% of the predicted HTCs were wrong, compared to, I think, 54% in the previous slide. So again, we're seeing that it's really common for the prediction to be outside the confidence interval of the measurement. In this case, it was much more common to underestimate the amount of heat loss, so these buildings were performing worse than expected. But the average gap across all was 31%, and this is an absolute gap. So actually, the trend line and the performance gap are really quite similar to this larger study. So I think we're starting to see that's nearly 600 buildings, still not a massive sample, but starting to see some trends emerge whereby RDSAP isn't terrible at categorizing buildings from best to worst. But if you think about individual buildings, it's a really blunt tool, and it's common to get really quite big differences between the two. So as a tool for stock analysis, you can see that it might be better for that application than if you think about individual buildings. So the next few slides, I wanted to think about why there's a difference between the prediction and the measurement. And I think one of the main reasons, or I think the main reason, is that building performance is incredibly variable. Here we've got a sample of a few thousand air permeability measurements from the Pulse database of just solid wall semi-detached houses. And here you can see that we've got a mean value of 8.9, but there's a massive distribution of performances. So even visually similar buildings have significantly different performance. And the way I was trying to get at that is to use a stat called the prediction interval. And the prediction interval describes, given the sample of measurements that I've had previously, how accurately can I predict what the air permeability of the next building will be? And effectively, every time we do an EPC, that's what we're doing. That's the question we're asking. So here, the prediction interval at a 95% degree of confidence is plus or minus 62% of the mean. So the air tightness could be 8 or 8.9 for these type of buildings, or it could be 62% less than that, or 62% more than that. So if you think all of those inputs go into calculating the HTC, and if we've got that degree of uncertainty in the inputs, even given perfect surveying, we should expect that there'll be differences in the output as well. Here I'm thinking about uncertain inputs again, and this time instead of air permeability, we're looking at U values. And this data is from previous U value studies, two done by the BRE, funded by the government, looking at SAP and trying to incrementally improve that. One by Historic Scotland, and again, the Building Performance Network State of the Nation report. And here we're looking at the difference between the mean measured U value, which is the blue bars, and RDSAP's prediction. And so you see that for several of those construction types, RDSAP is reasonably accurate on average. And if we went back to these charts where we're looking at HTCs, that could be part of that. That sort of explains why you can be right on average at HTC level. But if we think about the variation for buildings, for specific building types here, then each bar is a different study and it's a different wall type. And the error bars on there, again, this prediction interval. So how accurately can we estimate the next U value given what we know already? And here the prediction intervals are again enormous. For one study, the first one in the list there, it was plus or minus 20%. Now that was a study where it was looking specifically at standard solid walls, and they'd done quite a lot of pre-selection to try and select as consistent a wall as possible. And you still got this quite significant variation in performance. For others, the variation in performance is enormous. So if we've got this uncertainty in the inputs, even with perfect surveying, then we're going to have uncertainty in the outputs. So I think this is one of the key reasons why we see that performance gap. And it also has a sort of optimistic side to that. It means that if we put the right inputs into the calculation of the HTC and the EPC, we're really likely to get the right output. So if we can incrementally improve the inputs we put in and use measurements to calibrate EPCs, then we've got a real chance of improving their accuracy, and it will be the most significant improvement we can make to accuracy. So this slide is all about that point here. We've got a chart on the right-hand side, and we're looking at the impact of the calculated uncertainty in the main wall U value, which is from these studies here, on the EPC output, the rating for an example semi-detached building. And you can see that the uncertainty in just the main wall U value has an impact of between 5 to 9 points in the EPC rating. And again, I've chosen to show the rating, but I could have shown the predicted energy use, cost, emissions, any of those metrics. So the uncertainty in those inputs directly contributes to uncertainty in the outputs. And at the moment, pretty much all of our policy design and regulation is based on EPCs, and our quality assurance to a large extent is based on EPCs. But if we've got this uncertainty in the results, then okay, at a stock level, as I said, it might be a reasonable tool, but an individual building level, it really undermines any policy design that's thinking about building performance. So let's think about some conclusions. What can we learn from what I've been through? So I've looked at RDSAP here, but if you thought about any heat loss calculation method, 12831 for heat pump sizing, PHPP, HEM, they're all using predictions of U values, or assumptions of U values, estimates of U values, estimates of air permeability, although now we can start to put measured air permeability in. So they're using the same fundamental building physics, and I would expect the same issues to occur with any calculation method, which is why I put energy models like RDSAP. So we're looking at this larger sample of the performance gap now. The chart on the right-hand side includes the 503 from the Energy Savings Trust study that I started with, and the 80 odd from the other field trials. So now we've got a reasonable mix of new builds and older buildings, and we're thinking about the performance gap, the gap between the predicted and the measured heat transfer coefficient. And I'm using the same stats that I use to think about the accuracy of smart HTC. So the net mean bias error for RDSAP for this sample is 8%. So actually, on average, it's doing a reasonable job at categorizing good, medium, bad heat loss. And there isn't a significant bias towards over or underestimating the heat loss. There's a light bias towards underestimating the heat loss in this sample. But the precision, so this is the average difference that a measurement is away from the measurement, is only 38%. And that's quite a large number. It means that we've got an imprecise tool for individual buildings. And the outcome of that is that it's a useful tool for groups of buildings and stock level assessments, but it's a poor tool for individual dwellings. And a big problem with this is we're using EPCs to target our retrofit funding. And in that energy savings trust study I mentioned, they calculated that if the target was EPCC, not necessarily the ideal target, but if it just a target to get an idea of what the performance gap means, there would be £60 billion worth of funding directed to buildings which already meet that rating, so that are already got less heat loss than expected before we do anything. And so now you're talking about really big, meaty amounts of money, £60 billion worth of misdirected funding there that could be directed towards buildings that really need it. So if you thought about the sort of yin to that yang, there'll be buildings there which the EPC is saying these have got low heat loss, they're not a high risk for fuel poverty, and there shouldn't be a high target for retrofit measures, but actually their real performance is much worse than expected, and they won't be met by current policy tools. So the measurement gives you a way to allocate our funding in a much more efficient way. Also, it would be such a powerful tool for quality assurance. So at the moment, we're just assuming that the difference in performance that we calculate is delivered in situ. But we can see that there's so much uncertainty in the calculation of performance that really we can't have any confidence in that. So the measurement would give you a way to get much better quality assurance on what works and what doesn't work. And as well as thinking about individual buildings, a really powerful part of that would be we'd start to inform some feedback loops. So we would learn what building materials work, what processes work, and be able to repeat those and learn what went wrong with the ones that didn't work and not repeat those errors. And, you know, buildings are around for hundreds of years. So if we bake in errors into buildings that we're building and retrofitting now, it's got such a long tail over time. It also means that heat loss calculations like this are poor for heating and cooling demand sizing. They're a really imprecise tool for thinking about the heat loss of a particular building. So if you wanted to get your heat loss sizing right, then a measurement is a much more accurate way to do that, much more precise way to do that is perhaps the right terminology. And that sort of has a few impacts. I think the sort of research that's coming out now maybe says that missizing or oversizing of heat pumps in particular is not as big of a deal for performance as we feared it might be. But it still means additional capital costs if you're using a bigger system. It means that there'll be houses which we think are outside the range of a standard sort of normal domestic heat pump, which actually aren't. It also means that your emitter sizing would be off as well. So there might be houses which need many fewer changes to emitters than would be predicted by a heat loss calculation. So that concludes what I wanted to say about the performance gap and presenting these performance gap studies today. I've deliberately left a lot of time for some discussion and question and answers. So hopefully a few of those have been coming through. I'll leave this up for the moment, and then when we're sort of drawing to a close, then I'll show this next slide, which is about our next seminar next month.
Brilliant. Thank you ever so much for that, Richard. I know a few of you are having issues joining the link from Eventbrite, seem to be having a bit of a wobble. So we will be sharing the entire content from today, so you haven't missed out completely. I am now going to ask Rachel to just unmute herself and join in. I'm not sure if anybody's put any questions in yet, but if you do have anything that you would like to ask, feel free to raise your hand or just speak up.
Yeah, I'm afraid there's no questions in yet, but please feel free to put them in the Q&A box.
Or just put your hand up and we can have a chat. Bit down. You're number one, I think. Rachel, sorry, that was your job.
Yeah.
Hi, Richard. Can you hear me?
Yes.
Oh, fabulous. Yeah. How do we make them more accurate?
The calculations.
Yes.
Yeah. Well, we could swap to using measurements, or we could use measurements to calibrate the calculations, would be my message. So the reason that the biggest reason the calculations are wrong, in my opinion, and not the only reason by any means, is that the inputs are wrong. So if we improve the accuracy of the inputs, we would make an immediate impact on improving the accuracy of outputs. So measuring U values, measuring air tightness, measuring ventilation flow rates. That's what I'd say. Maybe you're all thinking, yeah, you would say that.
Well, no, I think you're absolutely right. I mean, that figure that you've got there of the EST study showing 60 billion, I sometimes feel that 60 billion was just wasted by us alone, because when I see things like, for example, the ventilation strategies being carried out on retrofit, and I mean, I must have been naive. In the early days, I thought a retrofit strategy is something that you would actually sit down and work out properly. But all I see is this blank strategy of let's rip out all the fans that are there and replace them. Let's cut some doors. It's very crude. But what I've noticed is so many perfectly good working fans. I've tested the airflow is more than satisfactory, but they're just being ripped out because the ventilation strategy says fit new fans. So, you know, just a tiny microscope looking at that, and we must have ripped out dozens and dozens. I can see where that 60 billion comes from. It's probably an underestimate.
Well, I suppose that's a key message there will be, after you've measured and you've seen the flow rates working, then take attention of the measurement and believe that, you know, a lot of the time measurement as a tick box can be worse than anything. Yeah. No, there's so much waste. Here we go.
Okay, I think Sally was next with a question. So Sally, if you want to go for it. Hi, Richard. Really enjoyed the presentation, and great to have some the collective background knowledge kind of put together in terms of the performance gap. This is something that us as energy advisors, I guess, and looking at buildings, particularly doing the early stage modelling and saying, how are these going to be, what's the prediction going to be, we tend to do an awful lot of air testing, as you say. I mean, I was interested in you saying that we should be verifying the data better, and but based on the research that you've done, you've shown that both for U values and also for air testing, actually there isn't a huge amount of correlation. And I think that's the reality of these projects. Anyway, that's a bit of a tangent. I guess what I'm interested in is, alongside air testing, we occasionally do in situ U value measurements, but they are so it's so difficult to get a representative value for the whole wall, particularly when we've got quite a lot of our existing structures are non-homogeneous, and you're measuring a point. So I'm really interested for alongside doing the airtightness test, which I think is kind of fairly essential in terms of the benchmarking and setting the starting position, what would you recommend is to take account of the fabric performance, and what does that look like in terms of what would it take to actually do that?
Yeah, the first thing we do is U value measurements. We've moved to using infrared U value measurements from heat flux plates so that we can try and measure across a whole wall surface and take account of that in homogeneous. You said the word much better than I could. I was confident I was going to say it right until I got to it. But yeah, the other advantage of using an infrared U value measurement is that you can do it in an hour rather than having to leave the equipment in place, which makes a big difference for how sort of scalable it is and practical it is to do it. So when we've done some example projects, we've done things like an HTC measurement plus air permeability and then U value measurements, and we try and cover one large area of every construction type. So one large area of wall type, and if you had two different wall types, and it'd be two different U value measurements. And it's quite fun for me to get the HTC calculation as is and gradually plug in your measurements and start to narrow that performance gap. And I had a slide all about how I did that for my house, and then people told me that it wasn't quite as much fun as I thought it was.
That's great, thank you.
Okay, we've got another question here, one from Lynn Partington, about, do we know the timescales of when HTC results can be used in RDSAP, or where we can actually enter this data at the moment? Yeah,
excellent question. And I would love now to tell you a date or a time, but we don't know. I can tell you there's a working group called the SMETA working group in DESNES who are really quite active at the moment. So it's definitely on the agenda. And you'll see that some of the software providers, I know Elmhurst, perhaps others, you can put a measured HTC into an energy performance report, but you can't do it for a certificate yet. So it's starting to give you some of the software to understand what your measured HTC means, but you can't yet put it into your EPCs, which is a massive frustration and something we've been working at for a long time. But when it comes to policy, the pace of change is risk averse, to put it politely. So hopefully in the next couple of years, says the optimist.
Okay, we've got another RDSAP question. So with the recent changes to RDSAP 10, how much difference do you think they'll make?
Yeah, well, you can put a measured air permeability in now, which I think could make a reasonably big difference. RDSAP is quite conservative on assumptions about air permeability. Basically, you end up with a range of between 10 to 15 meters cubed per meter square per hour at 50 pascals. So it can make a reasonable difference to put your measured air permeability in. Apart from that, the other changes don't touch the HTC, so they'll make no improvement. Really, it's putting in the measurements which will make the difference. You've seen that with these similar wall constructions and similar buildings having such variable performance, there's only so much you can do by looking at it. It needs that in situ measurement to really understand the performance.
Okay, so your next question is from Phil Norval, and he's asked, do you expect that a much larger number of measured U values will help inform the calculated heat loss figures in future, or do unique building characteristics mean you can never really accurately predict a particular U value from average figures?
Yeah, great question. When I go back a few slides to answer that. So here, these standard solid walls and where this X is, the point of these two field trial studies was to understand what was going on with solid walls, and it actually changed the assumption. So based on this field trial, the assumption in RDSAP was changed from 2.1 to 1.7 because the in situ measurements found that the heat loss was actually significantly less than expected. And the main reason for that was tiny little air gaps between the two leaves of brick. So in that case, the average was changed. And so that is a significant improvement. And that is why I think it would make a big difference to do, when I was saying informing those feedback loops, one of the things it would do to do measurements regularly would be to improve the model. So feedback into the model and say, and that's a really good case study of where we did measurements, found out something wasn't what we thought and changed the model. So the first part of your question, yes, I think it would significantly improve the models. The second part is, as you say, that the variability in these constructions is massive. So you would still have, it's easier to look on a distribution chart like that. You would still have a relationship like this, and your average wouldn't represent all of the buildings. You can only sort of do okay on average, and the buildings are just different to each other in ways that we can't see. So I think there'd still be a huge importance for in situ measurements for particular buildings.
Great. So the next question is from Andrew Brown. For funded work like ECO or GBIS, etc., installers will often only test if it's mandated or if there's a financial benefit. Is pay for performance or similar still a possibility for future funded retrofit schemes?
Yeah, that was so sad that we got almost all the way there and had it in the consultation, and then it died completely. I think that was a massive opportunity just to have it on some projects as on a trial basis in Eco4 and GBIS, so that when we got to the successor scheme, we would understand much better how the whole process works and be in a better position for it. But anyway, the consultation response very much said we're not doing it in Eco4, mostly because of time constraints. And a lot of energy providers has actually basically had all their projects to meet their allocation already organised, so they felt it wasn't practical. But it also said that they were very much thinking of it in successor schemes, and the SMETA working group that I mentioned is working towards that. And as I said, I'm an optimist, but I'm absolutely certain that will happen eventually. It's just, you just look at evidence like this and it's too obvious a thing not to do. So I'm sure it will come in eventually. And as much as I believe that there is such an enormous benefit to doing the measurements that it shouldn't need the mandate for it to happen, I can also observe that what you've said is true.
Okay, next question. What are the key emerging trends you foresee in the building performance measurement and retrofit in the next 5 to 10 years? And how is Build Test Solutions preparing for these?
Good one. Well, I think the major trend, two major trends, maybe looking at towards the same thing. The major trend will be to start using the measurements more. So air tightness measurements have had really good penetration, especially into retrofit in the last 5 years, where almost there'd been no measurements before. So I think that is sort of an example that we could look at for U value measurement and HTC measurement. And I'm sure that when we actually start doing measurements at more scale, this is a chart of 600 buildings in a country of several tens of millions of buildings. We'll learn a lot more about what measurements we actually have to do and what things work, and start to see those feedback loops. And when we see the feedback loops, I think they'll be so interesting and informative. And we might have to be a little bit brave to think about them, because there'll be things that we've been doing and materials we've been using forever without realizing they don't work. And we'll have to think about ways not to demonize that, and just to understand that we're all learning together. The other thing I think will happen is that almost every building has some data collection in it already. So smart meter data would be the obvious one from your meters, and we've developed a version. I sort of hinted on it at the start of the presentation I gave, that we've developed a version of Smart HTC which doesn't use internal temperature data, it only uses energy data, and it still gives markedly more precise thermal performance assessments than surveys. So using that data and gaining extra value from it, I think will be a real trend. And actually, there's a lot of temperature and relative humidity data being collected already as well. And things like smart thermostats are starting to leverage all that data. And the tricky thing is actually to sort of join the bits together for different households that are all using different manufacturers, and the data is stored in different places. But I think that'll start to happen at increasing speed.
That's great. Thank you, Richard. I think that's our final question we've got here.
Yeah, I think we've covered most. Is there anybody else that has a question that hasn't been answered? Feel free to.
I've got my hand raised, but you can't see my name for some reason.
Yes, go for it.
Yeah, sorry, I have been making my lunch at the same time as listening, so you may well have answered this already. So in principle, what you're saying sounds great, Richard. But obviously the implementation of it would have quite significant challenges, and I'm not suggesting raising standards isn't a good thing. It's just that the reality of doing that will probably have quite significant challenges. So I'm just thinking about things like the amount of time needed to do these additional assessment processes. That's obviously going to increase, and then the cost of doing that work is going to increase. There's already, a bit of a squeeze in the marketplace with assessment work. It's almost the race to the bottom as far as trying to get as many done as possible in the shortest amount of time possible. And then you've got to think about the skill levels of the assessors that are out there doing this work, and whether they have the necessary skill levels, and if not, what sort of training they need, and how long that's going to take, and to get enough people skilled to do the work that's required. And then you've got the regulation and oversight of all of this, and who's doing that, and how do they actually do that effectively and check that those U values are what they are. And it just sounds incredibly complicated. And the one of the effects of that is that this is going to slow down the time that we have to retrofit all the houses that need to be retrofitted in the time that we've got. And it's just, I don't know, sorry to sound pessimistic. I'm just wondering about those impacts.
Yeah. All right, so there's two sides to that, right? One is absolutely cost, and wrapped up in cost, you could think about the cost of complication as well. But the other side of that coin is value. And if there's an opportunity of £60 billion in this one example given, there is an enormous value to be gained by the measurements as well. And I think that's one thing that it's really easy to lose sight of. So we did a project about heat pump sizing, and we found that oversizing of heat demand was routine, but undersizing was also possible. And in that case, the cost of the measurement was really small compared to the just the capital saving you'd make in the equipment. And if you have undersizing, then you have to think about the cost of the risk of putting in a heating system that isn't large enough to service the demand of the building, and the cost that would have afterwards to go and remediate. So there is an enormous cost at not knowing how buildings work. So that's where the value is in measuring how they work, I think. And one of the aims, key goals that we've always had since the very start of BCS was to make the measurements as accessible and as easy as possible. And really, especially if you're integrating into existing systems, for the user, for the surveyor, there is no more cost, really. It's the cost of running the algorithm. So the possible cost of these HTC measurements is low pounds or pence per building. For a surveyor, if you're already there doing the EPC, you're already collecting way more building information than is required for the HTC measurement What you need is the energy data, which is already being collected at the meters, and the internal temperature data. And the sensors for that are really peanuts in terms of cost. So yeah, that's what I'd say about that.
Thank you.
No problem.
Thank you very much to both Richard and Rachel. I hope you all found that a useful and informative session, and I hope that you'll join us for the next webinar on the 27th of August, which will focus on proactively managing moisture with measured data in From Complaints to Confidence. Thank you once again.